very much for the introduction and also the opportunity by EPIC. I'm very happy to be here on behalf of our company to present to you our technology. So we are active in the field of adaptive optics. Our core technology is a deformable phase plate, as already mentioned in the previous talk by Maria. And so I will introduce you more in detail what is this DPP and why we think this can bring an evolution in the field of adaptive optics for ophthalmology. So again, I think this kind of overview was also brought up by Maria in the previous presentation, but to again place our technology compared to the other existing devices for adaptive optics or phase modulation in general, I have this overview here. So we have the very well-mature perfect technologies like liquid crystal, SLMs, or deformed mirrors for phase modulation. Liquid crystals having millions of pixels for very high order phase modulation, or deformed mirrors also working reflection. But also existed before this kind of tunable and adaptive lenses, which have their means of actuation outside of the optical aperture that sort of limits the amount of phase modulation, the complexity of the phase modulation that they can perform. But very good for example, focus tuning, very large amount of focus tuning. And that's where our technology comes. So what didn't exist before was kind of a refractive counterpart of these deformed mirrors, something which has like a 2D array of electrodes, but within the optical aperture, and that can provide very high order phase modulation. So here I have schematics. I can briefly discuss how it works. So there is a glass substrate. As you can see from the schematic, it looks already very similar to the continuous membrane deformed mirrors. So there is a 2D array of electrodes within the optical aperture. We have a big chamber, so it's an optofluidic device. And then there is a deformable membrane on top. And by electrostatic actuation, we can deform this membrane and modulate the optical path difference, change the amount of liquid in the optical path and modulate the phase of the incoming light. And that's by electrostatic actuation. So that's the electrode pattern of the current DPP. We have 63 electrodes, these hexagons within the optical aperture. And these are the sort of influence functions or the influence of the individual electrodes. If I actuate, for example, electrode 1, that's the sort of phase modulation which I can get. And the other electrodes, this shows how precisely we can modulate the phase of incoming light. And using these electrodes, we can replicate these Zernike modes. These are empirical Zernike modes, sort of similar to optical aberrations, up to 7th and some of the 8th order modes, both in vertical and horizontal orientations of the device. And so that's how a real DPP looks. So it's transmissive, unlike liquid crystals, it's polarization and diffraction independent. Because it's transmissive, we can even stack multiple devices together for performance enhancement. It's very thin, so the element itself is less than a millimeter in thickness. And so because of transmissivity, it also enables easy integrations and even retrofit into the existing setups. And another important factor about our technology is that it's based on wafer level manufacturing, so similar to the MEMS technologies. It's scalable, so if we need to produce a larger volume, bring the cost down by a large volume production, and that's also possible because the technology is based on microfabrication. And that makes our first product as Phaseform. So that's one of the deformable phase plate inside of a cage compatible housing, like 30mm cage housing, driving electronics and software. Some specifications. So as I said, it has 63 electrodes, can do more than 8 microns optical path difference. You're transmissive between 400 to 2200. And the current optical aperture is 10mm. And this product has been on the market now since 2022 in Europe, America, and multiple countries in Asia. So moving forward, what makes this technology interesting for adaptive optics. So I think Maria discussed more with regard to vision science, adaptive optics for vision science. Here I want to more talk about the retinal imaging, like cellular level retinal imaging. And as you know, our eyes are not perfect, especially so maybe in the normal daylight conditions when the pupil of the eye is about 2-3 millimeter. Still, they can do good imaging, but because of the limited numerical aperture, it's not optically sufficient to do cellular level imaging. And then when people dilute the eye, then the aberrations start getting worse, and then we are very far from diffraction limit. And then adaptive optics, of course, can be used to correct for these aberrations and improve the image quality. So this is a work, for example, by Wolf Harmoning, showing without adaptive optics for diluted eye, that's a sort of image of the retinal cells you can get, and that's when you use adaptive optics to actively compensate for the aberrations of the eye. And now image individual retinal cells. That's all and good, but what would be the real interest? So this is mostly for early disease diagnosis. So these very now, unfortunately, increasing number of people are having these diseases, which are blinding diseases, for example, diabetic retinopathy subject, or you can see an AMD subject or glaucoma. And the idea is with this image quality enhancement, with this cellular level imaging of the retinal cells, we can diagnose these diseases at a much earlier stage to start the prescription earlier and avoid progression of these diseases. So this has been studied in research for a while, so more than 20 years or even more. Adaptive optics has been used to really show this application. What is it? Why is it good? But mostly because it's been very complex, expensive, and also hard to retrofit into the ophthalmoscopes. It didn't go into many commercial ophthalmoscopes. So there have been companies which made ophthalmoscopes with adaptive optics, but it's still not very, very common and doesn't exist in every clinic. And so we think that's mostly because of the complexity and cost of it. So this is an overview of how conventional AO ophthalmoscope would look like. There is a wavefront sensor to measure the aberrations and a deformed mirror or an SLM for correcting those aberrations. And so what we can do and what we want to do is to replace this deformable mirror with a DPP, which we can make it much more compact, it's transmissive, or even retrofitting the existing setups, and can make it much cheaper, and also do the aberration measurement with sensorless algorithms without a wavefront sensor to further simplify the system development. And that's what we have tried. This is a work with a group of Kate Reeve at Institut Langevin in Paris. So this is a prototype for a full field OCT setup they have built in an eye hospital. So as you can see, it's already a very compact system. And what we did was to place one of our deformable phase plates right in front of the eye. So this experiment, the results which I'm going to show you, they have been achieved in 1 day. So without making any changes into the existing setup. So this ophthalmoscope existed there in the hospital. And I went there in 1 day. So we did integration of the hardware, one DPP. In fact, they also have a tunable lens for focus correction of the eye. And these are the aberrations that we corrected for. So up to 4 radial order and without a wavefront sensor. So this device had a time domain and a spectral domain OCT. We directly use the spectral domain OCT signal for the sensorless aberration measurement. And these are some results, in vivo measurements of volunteer. So here we have the DPP, the volunteer, and these are the retina cells. You can see without a DPP, so that's the resolution of the native instrument when there is no DPP in the system. And this is with DPP when we correct for the aberrations, and now we can improve the signal to noise ratio by twice and really resolve individual retinal cells. So this was a healthy eye. I think they had some eye surgeries, LASIK surgeries, but if there was some glaucoma, we could probably detect it earlier. So this was more or less the application I wanted to discuss and the benefits. We also have a Zmax model of our deformable faceplate because we consider it to be a new kind of a new optical element for optics designers, for system developers to evaluate what is possible, what can be done with this technology. We made a Zmax model. It's in the form of a DLL, very much similar to a DLL of a lens, which you can insert to the Optics Studio lens editor environment. You can import it just like that. It's based on the empirical DPP, so it has characteristics of the all optical layers, the membrane, the glass substrate, the fluidic chamber, and also the performance, the amount of Zernike modes that you can replicate. These are all based on a real DPP. So you can download it for free from our website. So very much encourage people to go and try to see what is really possible with this technology. With this, I come to the end of my presentation. So today I introduced you our deformable faceplate technology, a demonstration of its application in an ophthalmoscope for retinal imaging, and also the Zmax model of this device. So with this, thank you very much for introduction. We are also very open to collaborations, and I look forward to the questions. And yeah, thank you very much.